So now we have winding numbers. Each individual polymer could have a winding number with the barrier. Here's the barrier. Polymers, some of them go around it, some of them don't. They have interactions between themselves and say each plane. This is actually a simple model of a crystalline, a proposed braided phase of DNA that I studied with Randall Kamian a while ago. Covered up, it's 1996, so it really is a while ago. But we could ask what happens when I insert a barrier into such problems. And the winding and the entanglements, of course, will play a very important role in the dynamics of these objects. If it's actually DNA, it's charged, and you can imagine putting a perpendicular electric field to sweep the DNA. And if it's entangled around the barrier, that will impede the fluid flow, for example. So it's important to understand something about these winding numbers and their fluctuations. So here I've inserted a rod-shaped obstacle. And now it's just a simple generalization of what I showed you before. We just sum over all n polymers, and might be some very large number, like 10 to the 8th or so. And then I take this dot product. It turns out, again, just to give you the winding number of each individual polymer. And this is indeed something that looks like a vector potential of a long, thin solenoid, but it's now influencing not just one fictitious charged particle, but a whole bunch of them. And now it's a quantum many-body problem. And it turns out to be the quantum many-body physics of bosons. Why bosons? Well, these, of course, are actual polymers, 2 + 1 dimensions. But if you look at these entry points and these exit points, a natural thing to do is to integrate freely over all the entry points and all the exit points. And when you do that, you're basically getting a symmetrized Bose-Einstein wave function on either side of the matrix element. The analog of that matrix element is a matrix element of a Bose ideal Bose gas ground state. So it's bosons, don't worry about the details, but if I know the eigenfunctions and eigenvalues of a Hamiltonian that looks like this is a sum over the interactions of each of these directed polymers with the barrier, with this rod-shaped obstacle. This is the interaction between the polymers themselves. You might ask, does that pair potential between these polymers matter? And for the most of the problems that we're interested in, that pair potential acts in the plane. So you slide up and down. If they're nearly straight, then you can get away with a pair potential that just depends on the 2D position of these objects. And then here, this Hamiltonian that's going to control the winding number is basically a kinetic energy operator with a vector. Any questions? I've been racing through here. If there's something, if I haven't made myself understandable, please speak up.
So just a quick question.
Sure.
Does this analogy to bosons go all the way to kind of low temperature effective quantum statistics, like Bose-Einstein condensation, those kinds of things? So
it does. To actually get an actual phase transition of that kind, you would really need to put in periodic boundary conditions in the imaginary time direction. And if you do that, then you have basically physics on a torus. This is Feynman's way of looking at the superfluid phase transition in helium. So yes, there can be a phase transition in the winding number. And you can translate that, although I won't have time to talk about it today, and into the consequences of the universal jump in the 2-dimensional superfluid density of a Kosterlitz-Staulos transition. That tells you something about a universal jump in the winding number. So you can connect the two fields that way. I'll be mostly talking about free boundary conditions, and then that Kosterlitz-Staulos transition gets smeared out. But there are other transitions that can play a role. One of them is a Bose-Glass phase transition, a disordered cousin of a Mott insulator, which I'll again talk about. Other questions? Okay, let me go ahead then. So you can look at this problem again with the benefit of this Hamiltonian and try to figure out stuff. I'm not going to go into the details in this particular talk, but this was actually reviewed and explained in a paper with Addie Stern, who also spent some time at Harvard University, like Yaroslav. And what Addie and I managed to figure out was what this many polymer winding number looks like, what its fluctuations look like, even in the presence of interactions. And because it's so much like a superfluid, and in the limit that L goes to infinity, you're projecting out the ground state. So then everything we know about superfluid helium, you have boson world lines in 2 dimensions, can be taken over. So what do we find? We found that this mean square winding number for many polymers, not one polymer. Now each individual polymer can wind, but it's only going to wind when it's sufficiently close to the barrier. So only a subset of the polymers wind, and so you can interpret this result. Getting the 1/2 pi, that's hard work. But the basic idea is that there's a diffusion constant associated with each one of these polymers. Of course, they're avoiding the other polymers as well as the barrier. That diffusion constant is basically temperature, or kBT, if I put it in Boltzmann's constant, divided by G. That plays the role in projection of a kind of polymer diffusion constant. And then what this prefactor is it's the analog of the thermal de Broglie wavelength for these fictitious bosons. But in polymer language, it's just how far the random walker goes. If I have it wandering around a total distance L in the tau direction, this is the square. This product is the square of that quantity. It's a random walk, right? So it has a certain well-defined mean square size. That's what's in here. And then it multiplies the density of the polymers, the areal density, the cross section. And so that's counting the number of wandering polymers that have a possibility of entanglement. And so it almost has to have this form, and then there's this logarithmic divergence that we would get for even a single polymer out in front. And as I said, the hard part is to get 1/2 pi, but otherwise you can sort of justify it, at least after the fact, with some hand waving. But I want to tell you that, interesting though these directed polymers may be, and people have done experiments, X-ray diffraction, for example, off a liquid of a lined DNA, lined by, say, an electric field or a magnetic field. That, by the way, that liquid can have a hexatic phase. One of the interesting examples, we know that it's a hexatic phase would correspond to a superhexatic in this quantum analogy. But you can also study these things in high temperature superconductors. And I just want to give you a superconductivity 101 level explanation of why you can make this connection. Let's talk about superconductivity. And this is the beautiful PhD thesis of Alexei Aharonov in the early 1950s. He took Ginzburg-Landau theory of superconductivity. I'll remind you what that is, or tell you what that is in a minute. And he realized that if you just do some simple algebra with the phase of the condensate wave function that comes into that, and then any closed contour around here has to vanish, it turns out, and then there's a flux quantum, and you find a set, you find that in a magnetic field, as I'll describe it in a minute, the superconductor gets punctured by a set of approximately parallel vortex lines. It's the breakdown of the Meissner effect. So here's the Meissner effect. This is a superconducting phase diagram for a type 2 superconductor, is the fancy name. Aharonov predicted this set of materials before they were ever discovered. They were discovered in the early 60s, and people realized that, hey, this PhD thesis from 10 years before maybe was quite relevant experimentally. Before then, those experiments, people knew about type 1 superconductors, where you don't have this intermediate phase. But what Aharonov-Bohm predicted was a phase where the flux is expelled entirely below a certain lower critical field. There's an upper critical field, HC2, that's where you lose the superconductivity completely. And in between, as I said, superconductor is punctured by at regular lattice of these defect lines. Now, Aharonov in his brilliant thesis made a small numerical error and thought that the lattice would be square, but it turns out the correct error, it's triangular, which is what's been observed experimentally many times in these things. So what did he find in more detail? Well, first of all, I should say in 2003, he won the Nobel Prize for this nice work. So 50 years after he did his thesis and was told by his thesis advisor, Landau, that Landau didn't believe it, therefore he couldn't publish. Eventually he was allowed to be published. Just so you students out there, if your thesis advisor tells you you're wrong, just don't immediately agree with them. Because in this case, Aharonov was absolutely right. And finally, beautiful recognition 20 years ago. Okay, so this is a mean field theory of superconductivity, and I'll tell you more about that in the next slide. But you might ask, these are punctures, defects that are puncturing the bulk superconductor. If you put on a strong magnetic field, the magnetic field isn't uniform when it penetrates. It's in these quantized flux bundles, and what's fluctuating is the lines, which I think of as polymers, directed polymers. And in these directed polymers, this is the structure that Aharonov worked out of these vortices, and this is the condensate wave function. It goes to 0 at the core of the vortex. There's a superconducting coherence length at the side of that core, and there's a magnetic length. So some of the magnetism spills out beyond that core in a type 2 superconductor. And in any plane, these lines have a quantized vorticity, which rescaling to be plus or minus 1. And then, this is really wonderful. This happens to me all the time. They're just saying that to make you nervous, or make me nervous, I should say. But in any event, they interact with a screening two-dimensional Yukawa potential. And as Aharonov showed, it's a repulsive, purely repulsive potential. On top of any repulsion they might have associated with a columnar barrier. And then there's some sort of core energy. So that's the problem. And now, if you let these lines wiggle, which was only worked out much later, after Aharonov's beautiful analysis of this is the underlying Ginzburg-Landau theory in a non-zero magnetic field H. B is the curl of A, same A that appears here. Now it's a real vector potential, a real charge. E star is 2E. If you have Cooper pairing, and the actual phase diagram gets modified. It was first really understood, I think, and realized when you had the high TC superconductors, and what can happen is the Aharonov flux lattice can melt. And there are all sorts of intriguing phases. I want you to focus on the one in the that is shown right here, and that's when we have the superconducting analog of a polymer pneumatic. You have vortex lines wandering up, interacting with some kind of repulsive pair potential. This is a typical phase diagram for visco, bismuth, rhodium, calcium, copper oxide, with a magnetic field perpendicular to the copper oxide plane. And I want to ask you to think about this entangled vortex liquid. So, here, by the way, is illustration by, I think, American Superconductor, a company that was marketing these wonderful materials, superconducting tape. They haven't had an enormous number of applications. We continue to have New York Times articles about room temperature versions of these things. They're typically at high pressures and maybe not necessarily so useful. These are the TCs of visco and yttrium barium copper oxide. They are used in I believe, in magnetic resonance imaging pickup coils. They're very low noise and they can pick up very tiny signals and give you high resolution. So it's kind of a niche application of them. It also matters for other reasons. The fact that they have this melting. It's not going to work as a superconductor if, when you apply a magnetic field, the flux lines are free to move. Because, again, I have to ask you to accept this on faith if you don't know it already. What happens, you have a bunch of vortices like this, and that happen to be there because there's a magnetic field. If you now try to run a supercurrent through the material, the vortices move at right angles, and then their cores move and they dissipate energy. So this is a picture of a vortex line that's going from one side of the sample to the other, carrying 2 pi flux with it. And when that happens, you generate a voltage, and your material is no longer a superconductor. So if these lines are free to move as they wish, we'll stop them from moving momentarily. We'll show you how they do that experimentally. But if they are able to move, it's like, I would say, a little bit like a plastic crystal. If you take a very soft wire, a wire made of tin or even an ordinary coat hanger, it bends and moves because dislocation lines are moving through that object and allowing plastic deformation. That happens even more easily with these vortex lines. And so why would you care about that if you were trying to make an application? Well, suppose you were trying to levitate a train. Japan, so maybe the bullet train, we have floating on the rails with solenoids. This was a dream 25 years ago. So here's the train, and here's a solenoid. Suppose the solenoid is made of that American superconducting wire, and I make it into this nice helical loop. Now there's a magnetic field inside, but that magnetic field, if I just approximate the solenoid by a superconducting cylinder, it'll have a supercurrent going around like that. That's fine. That's what's going to produce the magnetic field that's going to levitate the train. But that magnetic field spills out into the superconducting wire. And if it will, if it's a type 2 material, and all these high TC materials are type 2, they have an Avogadro flux, basically penetration in the presence of this magnetic field, then the flux lines will move, dissipate energy, and your train will come crashing down onto the tracks. That's an issue with superconducting applications that's known for a long time. But now they found a very clever way, maybe not economically practical, but works in the lab, to stop this annoying motion of the flux. And this trick is called columnar pins, and it comes to us by a collaboration with nuclear physics. Nuclear physicists, as Aharonov-Bohm and others, discovered, again, ancient times, previous century, I have to confess, that you could make friends with nuclear physicists and have them use their heavy ion accelerators to do something remarkable. So you take this little superconducting sample, maybe a millimeter square, and you put it in this thing. This is like an 8-story building at the Weizmann Institute. And in this direction, they accelerate charged tin ions up to 580 million electron volts. And they shoot them at this poor, innocent little sample, and they puncture their own holes through them, holes of damage tracks. And these cylindrical damage tracks create locally normal metal, and that's where vortex lines like to go. And so you want to hold them in place. You want to stop them from moving so that you can have supercurrents go through this thing. This is the original experimental evidence. These are very intense magnetic fields of order 10 Tesla is the top value. And what they did was to irradiate various amounts of columnar defects, and you can easily get it to a regime where you have one columnar defect for every vortex. And I'll show you a little bit more detail, but this is the line without the irradiation, below which the vortex lines freeze in place due to point disorder, some kind of point pinning. Not nearly as strong, however, as these columnar defects. And then when you put in the columnar defects, the actual effective in a strong magnetic field, the effective superconducting transition temperature jumps up by 30%. 30% or 20%, whatever it is it really means something when you're trying to make these applications. And what they think, and what many of us think is going on, this amazing fusion of nuclear physics. They want to smash ions into each other. Here, we're smashing the ions into a superconductor. What happens is that if you do it right, they actually measure the dosage of these ions in Tesla, because that's the number of quantized Aharonov-Bohm flux lines. That tells you the number of lines that can be captured. And the ideal situation is where you have one columnar pin per quantized Aharonov-Bohm flux line, and then they don't whine, we don't entangle. They just sit there, and the material is pinned in place, these defects, and you have a good superconducting system over this somewhat substantial intermediate range of temperatures once you irradiate. So that was a real, I mean, it might be expensive to set up a factory to irradiate everything with this giant 8-story building. So maybe that's a practical limitation, but it was a great, in my opinion, great intellectual discovery. And so now you just have to add these columnar pins to all this winding number stuff that I've been telling you about. And so here betas 1 over KBT, and we treat these vortex lines, which of course come from quantum mechanics, but we can do an excellent approximation, treat them as if they're classical polymer pneumatic lines. And they wander around, and if they tilt over, they stretch a little bit. So there's a line energy, and that comes in, looks just like a mass. This is what I was calling G before, in some Lagrangian. This is the interactions I was talking about, that Addie Stern and I were interested in. And then this is now a new potential that has possibly a barrier. If I put on some sort of long repulsive column through these things that I'm trying to braid, perhaps. But it also has all of the interactions with the columnar pin. So both of these things, and then here's again this trick of taking a classical problem in 2+1 dimensions of classical polymers and mapping it onto quantum bosons in 2D. And so we end up with a kinetic energy operator. This is the one body potential that comes from the columnar pins, possibly from a barrier. And then here's their interaction with the two-dimensional screened potential that I was talking about earlier. And so again, it's Feynman's beautiful idea of slices in imaginary time to calculate this kind of trace of e to the minus some quantum operator. It's imaginary time, so I times t is what I'm calling tau here. And it was h bar in Feynman's original quantum formulation, but here h bar plays the role of temperature. And I can now tell you a little bit about non-Hermitian localization and many particle quantum mechanics. Non-Hermitian comes in because a natural thing to do with these columnar pins is to tilt the field a little bit. Then you're trying to unzip them from their natural direction parallel to the column. And I looked at this with Valerie Unifor and Enrique Tano, And this is the problem that you're left with when you add this kind of tilt, little perpendicular H field here. It gets multiplied by a flux quantum, divided by 4 pi, then there's this little h, and that enters at producing a kind of drift term in the statistical mechanics. So instead of just having this elastic energy here, we have a kind of drift term. This epsilon 1 tilde is like G, and they're trying to tilt. On the other hand, the columnar pins are going to try to keep everything as parallel as possible to the z direction. So there's this tension between tilting and wandering and then wandering along the columnar pins. That's going to be playing a big role here. So we can again work out effectively a boson Hamiltonian shown here with interactions, columnar pins, etc. And now we have something that looks a little bit like what Edwards was doing to calculate winding numbers. But notice there's an I here. So what we have generated by tilting a little bit is a constant imaginary vector potential. We need to understand the physics of these charged bosons, effectively charged with a constant imaginary vector potential. And that is slightly strange. First of all, you might think it's boring because if the constant vector potential, then the curl is 0. I can gauge it away. Well, it turns out that you can't under many interesting circumstances. And so we're led to explore the quantum mechanics, many body systems. I'll talk mostly about a single polymer with this tilt field in a world where we have non-Hermitian Hamiltonia that, as you'll see, are going to control the braiding. Any questions? Yeah.
Quick question. Is it interesting to make this transverse field dynamic? So then even the real vector potential would do something interesting?
Yeah, absolutely. So now you have a time-dependent, well, there are two kinds of time, right? There's imaginary time going this way, and I could have this perpendicular field somehow modulate. But I think you're asking if I take the strength of the tilt and I just put on an AC tilt, I think it would be an intriguing problem to figure out whether the flux lines could respond to that kind of thing as a function of frequency.
I'm trying to convert this vector potential to electric field.
Yeah, I understand. And I think the analog of an electric field would be if this H, if this constant little h were tau dependent. That would be the analog of an electric field.
Right.
And we have to figure out how our experimental friends could do that in some tricky way. But it would be intriguing if one could imagine doing that in a laboratory experiment, especially. Other question? Okay, so there's all these cases to consider. I'm not going to go into all of them, but you see how these spaghetti possibilities. This is the original Avogadro flux lattice. We want to understand what happens when I put in a barrier. Let's say here's a barrier. What's the winding number going to look like? What's the winding number going to look like with columnar pins? And again, as a function of this tilt field and so forth, you can get lines that are melted and winding even in the presence of this columnar pin disorder. So there's the melted Avogadro flux lattice, so no columnar pins up here. Avogadro flux lattice melts, go to high temperatures, available to high temperature superconductors. This is called the Boson glass phase. It is the Boson glass phase because I've got one flux line per columnar pin and it locks. And in fact, if you take this Boson glass phase and you put on a perpendicular magnetic field, nothing happens because it's so happy to sit and still remain in the columnar pin. And there's a critical threshold where they start to tear away. So this robustness of the Boson glass phase is sometimes called the transverse Meissner effect. You tilt enough, though, you can pull them away and now have a forest of columnar pins with a tilted, wiggly forest of essentially polymer pneumatic in the form of these vortex lines. So there's a flux lattice, there's a multi-flux liquid, and we want to understand what is going on here and how does it affect those windings. So here's this experiment. Unfortunately, hasn't been done, but this is what we were hoping our experimental colleagues with access to heavy ion accelerators would do for us. We wanted them to create a defect, the analog of a barrier, columnar barrier. We wanted them to create windings for us and study the flux flow resistivity and so forth. And one way to do that is to put, have a mask for your heavy ions and only let most of them go through a hole. And then you have a column of columns, a column of columnar defects. And this is going to be the boson glass. Any flux lines in there are just going to get trapped. And so it's basically, you have a perfect, beautiful superconductor here. We will shortly run a current. See what happens. That's going to come in one slide, roughly. Then outside, there might be some columnar pins and then wandering flux lines. And we can ask, how do the ones outside wander around this essentially impenetrable area? So dense columnar pins produce an obstacle, basically. And now we're going to ask, how does this flux line and all its relatives that are out there away from the columnar pin, how do they behave? So with Addy and others, we thought about these winding numbers, and a very cool thing to do is to take this problem, which is what Edwards was interested in, but with many basically directed polymers involved, and I want to tell you what happens when I run a current vertically through the this barrier. Now, this barrier is a well-pinned type 2 superconductor, so it's going to conduct a current with no problem, no dissipation. So I can just tune up a current and redo the problem and try to see what happens. So, no current. What do you think is going to happen when I turn on the current? Any suggestions from this audience? Random guesses are, well, yes. Very good. So I throw the switch, I run the current, and if this thing would advance. Oh, of course, I've forgotten how to do it properly. I can now do it properly. Yes, you guessed right. Well, of course it wasn't. Figured it out. So yes, now the average winding number is non-zero. Not just winding number fluctuations squared. They are winding, and wouldn't this be a great way to stop the flux flow resistivity in the bulk sample? Wind them around these guys, an expense of, needless to say, of drawing a current that way. Now, if they were to have to go at right angles in the XY plane, if they wanted to move, they'd be braided, they'd be entangled, and you might even have a superconducting device that would work well away from the columnar pin. So that's the idea. And I can simplify this. This is well, it's at about 15 minutes, I think. Does that sound right? So in the remaining 15 minutes or so, I'll tell you about winding numbers and localization lengths when we have a simplified situation where the current goes through the middle here, and the superconductor is a cylinder, might be a fairly narrow cylinder, filled with columnar pins. And now I want to ask, what sort of winding is even one polymer going to do in the presence of this disordered potential? And this will bring us, as you'll see, a close connection with non-Hermitian Anderson localization. So I'll tell you or remind you about it as we go along. So just to set the stage here, if I didn't have any columnar pins, I didn't have any current as well, this would be just the problem I started with, where now the barrier is some giant circle that defines the inner wall of this annulus. And this is basically a random walk, free energy for a freely jointed chain. And there's an effective diffusion constant here. And if you work out the winding number, you can get the, basically the kind of result that Sam Edwards got back in the 1960s. What is it? It's basically a length, which is a diffusive length of this thing wandering now basically in one dimension around the ring. And this numerator is how far it wanders in a cylinder of length L with an effective diffusion constant that's again temperature over G or kPt over G. This is how far it wanders. It's a random walk after all. This is the total circumference. And so it's going to wander around in a random walkway around this some number of times. On average, it will be 0 without the current. And I square it and it all works out. You get this very nice intuitive result. Okay, but now if I add a columnar pin, no current yet, a single columnar pin, perhaps, or a bunch of columnar pins, the quantum mechanics, as you'll see, will be the quantum mechanics of a boson, a single boson, in a random potential, in one dimension. It goes around this cylinder. And a lot is known about that. And in particular, you can work out the winding number based on the eigenfunctions of, could be an electron, or it could be a flux line, or it could be a boson in a random potential. And many of you might know, but if you don't, I'll tell you that when you have a random potential in one dimension, Phil Anderson showed that you can get electron localization, but in this case, it's flux line localization due to the randomness of the potential. It finds the local minimum and it gets trapped there. And of course, the winding number is going to know about that. If I have this flux line in a localized state, it's not going to want to wind. And so you can show that the winding number of fluctuations, no current, that's coming in a minute, they now decay exponentially with this localization length. So Xi is a localization length, it's still proportional to L, as it is up here, but there is a exponential localization. The thing just doesn't quite refuse to wind, but it grudgingly winds an exponentially small amount when I look at the mean square. So there's very straightforward now to put in a current threading through this thing. And of course, that current is going to produce a perpendicular magnetic field out here at radius r. And it's going to try to tear the flux line away. But we have to ask ourselves, will Anderson localization survive this tilting? And this is the classical energy that you would write down in 2+1 dimensions for a single directed polymer. And now look at the slope. The RD tau is trying to match itself with this slope, with this effective perpendicular magnetic field, which I call little h. Little h goes like h perp. And in fact, with the current, it goes like the current divided by 2 pi times the radius of this thing. So there's a little h that's going to try to delocalize things. There's a quantum Hamiltonian, just like everything else, but it's non-Hermitian. And so here it is with its constant imaginary vector potential. I'd love to make it tau dependent. We'd have electric field maybe, but I haven't thought much about that. Here's the disorder potential. It's a one-dimensional problem with periodic boundary conditions. It's the world's simplest non-Hermitian quantum problem, I think. So what happens when we apply this current? To figure that out, I need to put on this H. That's what the current does, and try to explore things. And one thing you can show quite easily is now there's a winding number that's non-zero. This should be actually the average of W. That's proportional to the current. There were no current, winding number would vanish by symmetry, but the coefficient of how much it winds given a certain current, the linear response is determined by precisely those fluctuations that I've been telling you about up till now. So we know a lot about what's going to happen. In particular, if I have a disorder potential, then in fact, the actual average winding number is really tiny for a big ring, so there's going to be almost no response. That's the transverse Meissner effect. It's the presence of a disordered potential. And so, not escape your attention that this looks like a barber pole. And so there is a tension between the tendency of the current to take the vortex line and wind it like a barber pole, instead of having it lock in to this columnar defect. And this is a tight binding model that is designed to sort of get at this question: does it tilt or does it not tilt? And it's done in terms of boson creation and destruction operators that are living at the sites of this columnar pin lattice. We simplified the problem in the way that actually Phil Anderson originally did, and put an on-site random potential, but you get the same results if you have random hopping. So this is an on-site random potential through the columnar pins, and this T is just a kind of 2+1 dimensional imaginary time version of a tunneling matrix element to go from columnar pin to columnar pin. And of course I could put a barrier too, and what you can, well, basically I have done a barrier because this hole, no flux lines allowed in there, so there is a barrier, just as in the original Edwards problem. And now for the single flux line, you can work out that the entry point, I'm now using X to measure where the flux line is around the ring. The entry point subtracted off from the exit point divided by 2 pi r, that's just the winding number. You can show that by this mapping that turns out to be proportional to the derivative of the ground state energy of the equivalent quantum problem with respect to this imaginary vector potential. At first, nothing happens, but eventually, what Naomichi and Tano and I found is that this winding number, W of H, undergoes a phase transition as a function of the strength. It refuses to wind like a barber pole for small h. There's a critical value of h, depends on the disorder, beyond which it breaks free. And it goes from being a localized state to an extended state that goes around and around. So there's actually a phase transition in this 1D problem. In ancient times, I won't go through all the details. This is Phil's classic paper. The wisdom was all states are localized in one dimension. There's good physical reasons for that, for Hermitian Hamiltonians. If the Hamiltonian is not Hermitian, as things here, that's no longer true. I'm going to wind up by just saying, okay, what Naomichi Tano did was to take this Hamiltonian and compute the spectra and the eigenfunctions and the tilts associated with all the wave functions of this problem. He did that numerically, although you can also do some analytic stuff. And here's the spectrum. It's a non-Hermitian problem, so the eigenvalues are in the complex plane. They have a real part and an imaginary part. If G is basically H, so it's the thing that is tilting. If there's no tilt, all these states, all these little dots here, they're all localized states. Now you put on the tilt, and you get this bubble in the complex plane, a bubble of complex eigenvalues. These states are all delocalized. And so you can work this out in terms of winding number. I'm just finishing up here. The winding number divided by the length is what Naomichi essentially measured here. And for these various values of H, there's a winding number that sort of smoothly varies with eigenfunction. But when you get out to the top of the band, things are much more robust. Also, the bottom of the band, you stay localized much longer, but eventually everything tears free. And you can measure the tilt slope associated with these eigenfunctions. There's this beautiful picture. I can say it's beautiful because Naomichi did it, I did, where you actually follow the trajectory of a wave packet that starts out maybe over here. What happens is it gets trapped. For large time, you go to the ground state, you go to the lowest energy localized state, and it gets trapped. Tilt field caused by this current is small enough. But if you go above that critical tilt field, it starts to look like a barber pole. So this is the essence of this non-remission phase transition view as probability distribution and stuff. So I'm going to conclude by saying, I don't know about you guys, but I've written about 300 papers, if you can believe it, in my life. And as someone once told me early in my career, you can write a paper, you can cast it on the waters of the sea of knowledge, and it will sometimes sink without trace. Despite the fact that you like that paper. Now, some of my papers didn't immediately sink. They seem to have had some effect. But there's one with Amici is a kind of sleeping beauty. I discovered this thing called sleeping beauty in the archive. The paper can lie dormant and then jumps up. So I never had a sleeping beauty paper, but this one might qualify. And Paul Ginsberg sent us this. This is the number of downloads of our paper. And Amici, who's very modest, very nice person who never bragged about himself, but he liked this because and in recent years, Sleeping Beauty may have found Prince Charming. I don't have time to tell you about neural networks. There's weird spectra there. If anybody's interested, I can tell you in the question period. Let me stop and thank you for your attention.